So far, we have illustrated everything with sentences written in English. English is a good language for expressing logical information in many circumstances. However, it's not without its problems. English sentences can be grammatically complex, and they can be ambiguous. And failing to understand a sentence can lead to errors in reasoning. Even very simple sentences can be complex. Here we see two grammatically legal sentences. They are the same in all but the last word, but their structure is entirely different. In the first sentence, the main verb is blossoms, while in the second sentence, the main verb is sank, and blossoms is a noun. As another example of grammatical complexity, consider the following excerpt taken from the University of Michigan lease agreement. The university may terminate this lease when the lessee, having made application and executed this lease in advance of enrollment, is not eligible to enroll or fails to enroll in the university or leaves the university at any time prior to the expiration of this lease, or for violations of any provision of this lease, or for violation of any university regulation relative to residence halls, or for health reasons, and so forth. The sentence in this case is sufficiently long and the grammatical structure sufficiently complex that people must often read it several times to understand precisely what it says. As an example of ambiguity, suppose I were to write the sentence, "There's a girl in the room with a telescope." Here we see two possible meanings of this sentence. Am I saying that there is a girl in a room containing a telescope? Or am I saying there is a girl in the room and she is holding a telescope? Such complexities and ambiguities can sometimes be humorous if they lead to interpretations that the author did not intend, as in these infamous newspaper headlines with multiple interpretations. Crowds rushing to see Pope trample 6 to death. Who would have guessed that the Pope could be so cruel? British left waffles on Falkland Islands. Is the British left unclear on what to do? Or do the Brits simply not like waffles? Scientists grow frog eyes and ears. Food stamp recipients turn to plastic. Fried chicken cooked in microwave wins trip. Indian Ocean talks. I always imagine it as a deep voice. Using a formal language eliminates such unintentional ambiguities, and for better or worse, eliminates unintentional humor as well. As an illustration of errors that arise in reasoning with sentences in natural language, consider the following examples. In the first, we use the transitivity of the better relation to derive a conclusion about the relative quality of champagne and soda from the relative quality of champagne and beer and the relative quality of beer and soda. Champagne is better than beer, beer is better than soda, therefore champagne is better than soda. So far, so good. Now consider what happens when we apply the same transitivity rule in the case illustrated here. The form of the argument is the same as before, but the conclusion is somewhat less believable. Bad sex is better than nothing. Nothing is better than good sex. Therefore, bad sex is better than good sex. The problem in this case is that the use of nothing here is syntactically similar to the use of beer in the preceding example, but in English, it means something entirely different. Logic eliminates these difficulties through the use of a formal language for encoding information. Given the syntax and semantics of this formal language, we can establish simple symbolic manipulation rules that produce all and only logically entailed conclusions. In this regard, there is a strong analogy between the methods of formal logic and those of high school algebra. To illustrate this analogy, consider the algebra problem shown here. Xavier is 3 times as old as Yolanda. Xavier's age and Yolanda's age add up to 12. How old are Xavier and Yolanda? Typically, the first step in solving such a problem is to express the information in the form of equations. If we let x represent the age of Xavier and y represent the age of Yolanda, we can capture the essential information of the problem as shown here. x equals 3y or x minus 3y equals 0, and x plus y equals 12. Using methods of algebra, we can then manipulate these expressions to solve the problem. First, we subtract the second equation from the first. Then we divide each side of the resulting equation by minus 4 to get a value for y. Finally, substituting back into one of the preceding equations, we get a value for x. Now consider the following logic problem. If Mary loves Pat, then Mary loves Quincy. If it is Monday and raining, then Mary loves Pat or Quincy. If it's Monday and raining, does Mary love Quincy? Yes. If it is Monday and raining, does Mary love Pat? Maybe, maybe not. If we learn that Mary loves only one person at a time, is it the case that if it is Monday and raining, that Mary loves Pat? No. How do we solve a problem like this? As with the algebra problem, the first step is formalization. Let P represent the possibility that Mary loves Pat. Let Q represent the possibility that Mary loves Quincy. Let M represent the possibility that it's Monday. And let R represent the possibility that it's raining. With these abbreviations, we can represent the essential information of this problem with the logical sentences shown here. The first says that P implies Q. That is, if Mary loves Pat, then Mary loves Quincy. The second says that M and R imply that P is true or Q is true. That is, if it's Monday and raining, then Mary loves Pat or Mary loves Quincy. Our job is to prove that M and R implies that Q is true. That is, if it's Monday and raining, then Mary loves Quincy. Given this formalization, we can use a reasoning rule analogous to the rule for subtracting equations to answer our question. We notice that P occurs on the left-hand side of one sentence and on the right-hand side of the other. Whenever this occurs, our rule allows us to cancel the P and thereby derive the conclusion that if it's Monday and raining, then Mary loves Quincy or Mary loves Quincy. Dropping the repeated symbol on the right-hand side, we arrive at the simpler conclusion that if it's Monday and raining, then Mary loves Quincy. We can use a similar approach to show that if Mary loves only one person at a time, that Mary does not love Pat. This example is interesting because it showcases our formal language for encoding logical information. As with algebra, we use symbols to represent relative aspects about the world, and we use operators to connect these symbols in order to express information about the things those symbols represent. The example also introduces one of the most important operations in logic, namely resolution. In this case, a restricted form of resolution. Resolution has the property of being complete for an important class of logic problems. That is, it's the only operation necessary to solve any problem in this class. This exercise tests your understanding of formalization using these logical operators.